Does this work? Yeah. All right. So welcome back to yet another live stream. Today we are going to continue with the implementation of the one, or at least we try to continue the progression of the 1 billion row challenge on Linux on x64. We are again SSH'd into an Arch Linux machine, which sits right underneath me. And yeah, I don't think we should waste any more time, and let's get to it. So yesterday we were exploring how Linux perf works. I think for now we just don't really care about this, and yeah, so probably we just say if 0, we just don't use it for now, and if so, remove all of the counting stuff. All right. So now we also don't have a cycle count. Let's see if it builds. Build. Okay. All right, it builds. Now, does it also run? Yeah. So if we call time on this. Okay. So as you can remember from yesterday, maybe we were structuring our code such that we spawn all of the threads in the main function and join them together so that they all return. And each thread then determines which chunk to work on based on its lane index. Now we also looked into how we can measure our code. And we can either use perf, which obviously causes us to go into kernel space from user space, but we can also use an instruction on x64 without leaving user space, which is called RDTSC, read timestamp counter. Now RDTSC does exactly what the description here tells us. It reads the current value of the processor's timestamp counter, a 64-bit MSR, model-specific register, into the EDX, EAX registers. The EDX register is loaded with the high-order 32 bits of the MSR, and the EAX register is loaded with the low-order 32 bits. On processors that support the Intel 64 architecture, the high-order 32 bits of each of RAX and RDX are cleared. Now, what does this tell us? Basically, the RDTSC instruction puts 32 bits into EDX and 32 bits into EAX, and we have to assemble it together to get a 64-bit value. Now, we could either, last time, Intel Intrinsics guide, we used the Intel Intrinsic RDTSC, which already puts those two 32-bit values together. But we can also do this ourselves, and I think this might be interesting to do. Yesterday we said we put all in a single source file, but yeah, maybe we don't. So let's write some assembly code into 1brc low level.asm, and here we can define our function raddtsc. This is basically a global definition which will get exported in the final object file. Then we have to declare that we are now entering the section, the text section, which contains all of the code. And then we can say our raddtsc function calls raddtsc, the raddtsc instruction. Now, how do you do comments again? In NASM comments. Now, RAX contains the low 32 bits of the MSR. RDX contains the high 32 bits of the MSR. Now what we have to do is we have to shift left RDX by 32. So we have to shift the 32 high bits, which are in the low bits of RDX. We have to shift left them by 32. Then we OR them. Then we OR RAX and RDX together, so that everything is contained in RDX, and then we return. Because of the calling convention, RAX is the return value, and therefore we are good to go. So this is our raddtsc function definition. How can we use this in our C code? It's actually pretty simple. I already had it here. We can declare an extern function, which is in another compilation unit here in this object file. And we say extern raddtsc, it takes nothing, and it returns a U64. Now in our build, we also have to consider the consider the compiled object. Now we want to compile our assembly file 1brc low level. We want to compile this using NetWide Assembler, NASM. Now NetWide Assembler wants a format, NASM-H-F, and here we choose the format ELF64, which you can see Linux, 64-bit Linux. We are on 64-bit Linux, so NASM-F ELF64. Then we can also define where NASM puts the output, which may just be 1brc low level.o, and we also have to give it the source file, which is 1brc low level.asm. Okay, label instruction prefix. Now NASM doesn't like this. How do we make a comment in NASM? Like this? I don't know. NetWide Assembler comments. A semicolon. Yeah, it was a semicolon. Okay, now it works. Now we have the object file. Read elf. Do we have that? Read elf 1brc low level.o. Okay, that didn't work. File 1brc low level.o. This is an ELF64-bit LSB relocatable. So yeah, does that work? Read elf. Let's see. Read elf symbols. Read elf symbols. 1brc low level.o. And as you can see, it contains the RDTSC function. Now, how do we get all of this together? Well, first in our build script, we can actually put this in here, nasm-f elf64 -1brc low level.o and 1brc low level.asm. And then we can just pass this to clang 1brc low level.o, and it should work. If we now build this, great, that builds, and now we can use the RDTSC in the RDTSC function defined in our assembly. Use start time start TSC is equal to this, and use 64 elapsed TSC RDTSC minus start TSC, and then we can add our printf TSC elapsed LU elapsed TSC. We can build this. Oh, this is not a function. And then we can run it. And as you can see, we get the 7.5 billion as we did before. So this works. Now, what we probably also want to do is we want to know how many cycles, what's the frequency of this timer. So how many ticks per second are elapsing. And for this we can write a function. And we can name this estimate TSC frequency or something like that. And estimate TSC frequency takes nothing. How we do this is we measure the elapsed TSC ticks against another clock. Now in Linux we have another, if we say man clock get time, we can use clock get time with clock monotonic to get a different clock. And then we can time this clock against, we can time RDTSC against this clock to see how many ticks per second are elapsing, because we know the clock frequency of clock monotonic. Okay, so first we have to maybe also set OS get time, and this calls clock get time with clock monotonic. Now this also wants a clock ID and the struct time spec. Struct time spec time, reference to time, it will start in there. And then we probably also have to pound include time. Yeah, we have to pound include time.h. Yeah, and struct time spec. Okay, time spec now contains the TV sec and TV nanoseconds. Okay. So if we want to get, so we get the resolution as nanoseconds. Now nanoseconds, you have milliseconds and then nanoseconds, right? So that's 1 million, right? Is that correct? I don't know. So let's say U64 result is equal to time.tvsec times nanoseconds in seconds. So this is, no, it's 1 billion. So you have milliseconds, microseconds, and then nanoseconds. Okay, so we have to multiply this by 1 billion to 3, 1, 2, 3, plus time.tv and sec. And then we can return the result. Okay, we probably also want to provide a value time to wait. And yeah, so we start by getting the start time, which is always get time. And current time, always get time. Or we can do something like do current time is equal to always get time while current time minus start time is less than time to wait. Now then we once get the timestamp counter start TSC, then we get the timestamp counter again, RETSC, we get the elapsed is equal to NTSC minus start, TSC, wall time elapsed is equal to end current time minus start time. And well, now we can just get the ratio of the two. So if, for example, the wall time is 1 second, and so that's 1 billion nanoseconds, and 7.5 billion or 3.5 billion TSC ticks have been elapsed, then we have a frequency of 3.5 gigahertz. Yeah. Now this will be measured in if we just take the ratio TSC elapsed, if we just take the ratio over as an F64, we get it in gigahertz, probably, right? This will be in gigahertz. Is that a problem? I don't know. TSC frequency. Okay, so this will return an F64. Is that what we want though? Yeah, let's just stick with it and see what happens. So let's do an estimate frequency. Estimate frequency. Or let's call this CPU frequency. And let's wait 100 millis. Let's say pound define milliseconds micro nanos. So milliseconds is 1000 times s is 1000 times s. S 1000 times micro, and this is 1000 times no, millis micros yeah, this one works. So let's estimate the CPU frequency using 100 milliseconds. So that's 100 times in nanoseconds. 100 times 1000 times 1000. Let's say, okay, use 64 time to wait 100 times 1000 times 1000. Time to wait, and F64 frequency, CPU frequency. So let's see frequency %f dot 5 and we also have the TSC elapsed. And then CPU frequency. Let's see what we get. Yeah, we get a CPU frequency that's pretty close to 3.4 gigahertz. Now we probably want this in hertz. We probably want this in hertz. So we could just multiply this, but we so we want this per second. So wall time elapsed over equals, and that should do it. Infinity. Current time minus start time. One, two, three, 1, 2, 3, 1, 2, 3. I mean, this should theoretically yield something different, but TSC frequency times 1. Does that work? Yeah, so now we have it in. I don't know how accurate this is though. don't know why we can't divide, but okay. Yeah, so let's 1E9 and now we can, if we have the frequency in hertz, we can now just do a simple divide. We can elapsed seconds. We can just do a divide by the frequency. Yeah, this has to be a float. And let's do .2 and 2.2 seconds. We could also get it in milliseconds if we multiply this one by 1000, and so on and so forth. Yeah, so this we can now theoretically use to time our code. Yeah, we could also do millis 100. No, micros 100. Here. It doesn't make sense. Whatever. Okay. So this way we can time our code, and we can also measure the throughput, which is then defined as, so let's say throughput, the actual chunk size, so it's gigabytes per second, elapsed seconds. So let's not do this. So time throughput dot for f seconds in gigabytes per second. Now chunks, yeah, we would have to multiply this by GB1. And then use the elapsed seconds and the throughput. So we're currently doing 5.8 gigabytes a second. Which makes a lot of sense. Because our file is 13 gigabytes large. If we are now increasing the lane count to, let's say, 2. Oh. We had 2 outputs, and as you can see, the throughput is a little bit lower. If we increase it even further, we get even lower throughput. So we get diminishing returns as we increase this lane count. Yeah, and at 10 we only have 2.5 gigabytes a second. Okay, so let's reduce it to 1 again, and let's actually do something. And let's remove all of this stuff. We can pull it back in if we want. So by placing RDTSCs in your code, you can get your timings, and then you can time specific parts of your code. Now, what is the next thing we do? So let's actually do something. Let's actually do the challenge. So the challenge requires us to parse the CSV file. Let's make a quick recap. head-n10 measurements.txt. Here are the first 10 lines. As you can see, we have a city name, and the city name can be between. So we have, let's quickly write that down. Does that work? Oh yeah, this works. So we have this, and then \n city name. The city name can be between 1 and 100 bytes. Temperatures are in the range -99.9 and 99.9, although that is pretty unrealistic, to be honest, and have one fractional digit. So that is an assumption we can also make. Up to 10,000 station name, individual stations. So this is also an assumption we can put into our code. Now, let's actually start and parse the lines. So for the case where we just have one lane count, one thread executing this, we don't have to adjust the chunks. As you remember, chunks may not start at a new line, which would require us to scan for the first new line in the chunk and then start from there. Now, as we just have one thread for now, we don't really care about this. So first and foremost, we should probably find the new line character. We can write a function here that that returns the pointer, and we can say, okay, find character, and the find character function takes in a maybe a source, or maybe this is often referred to as a haystack, and it has a length. Let's make that U64 length, and then we also have a needle. We want to find the needle in the haystack. And then we just go through all of the characters. It's a pretty simple, non-optimal approach, of course, but whatever. U64 index I0, I is less than length, and I++. Now, if haystack at index I is equal to the needle, then we return, so let's say U8 star u8 star result is equal to null. u8 result is equal to haystack at I or plus I. We use pointer arithmetic and then we do a break and return the result. So when we found the needle, we return the pointer. So u8 star new line. We probably want to do this repeatedly. So while 1 for now. We find the new line, find character in our we probably also want to keep an offset, but maybe current cursor or something. Cursor is equal to chunk adder. Do we want to find the new line? I mean, we could start and find semicolon cursor semicolon. This will give us a semicolon, and then we can calculate the length, city name length, or name city length is equal to semicolon minus cursor. Okay. Now we know the length of the city. We also now want to find the next new line, find character, cursor, let's set cursor is equal from semicolon plus 1 from semicolon plus 1 to the new line. So u8 star no. We could set just cursor to this. u8 star new line. And then we can also get the length of the digit. Temperature length is equal to new line minus semicolon plus 1. And with this information, we could theoretically parse. I mean, let's just do this break, and let's print both the city name and the temperature. So city name is from cursor with the city length, and the temperature is temperature length starting from semicolon plus 1. Okay, build this. Now find character. Oh yeah, it needs the length of the haystack, of course. So the length of the haystack and cursor is equal chunk adder plus the chunk end. So while cursor is less than end cursor, we can do this. and the remainder is end cursor minus cursor, and semicolon +1 minus cursor. Counter, we don't need this. Okay, as we can see, we get the correct city and temperature. All right, so the next thing we can do is actually parse the temperature. Let's make a function for this. Parse, let's return a float for now. And it takes a U8, the string and the string length. We could also construct a string type here. Yeah, we may want to do that. Okay. So first we have to find probably the dot. Yeah. First we find the dot. Find character stir length and the dot. Now this, of course, this code has a lot of bugs here. If there is no semicolon and curse, and yeah, we have a problem because we don't check for null, but we can add that later. So dot. So integer length is equal to dot minus stir. What we could now do is for int I is equal, we could start at the dot. Okay, we could say u64 mol is equal to 1. We could start at the dot. Now we start at string. So for int I0, I is less than integer length, I plus plus. What we can do, so result or integer, this is the integer part, and what we do is we subtract the stir by, so stir at I, this is the digit. As you know, ASCII characters are contiguous, so 0x30, 0x31, and if we subtract 0x30, we just get the digit. And what we can do now is integer plus equals digit. And first we do a mol integer times equals 10, and then we add the digit. So each time we go around, we multiply by 10 and add the digit. So for example, if we have a 99, we see the 9, we multiply, I think it's 0, right? We multiply by 10, so we get 0. We add the 9 in, then we have 9. Then in the next iteration we get another, we multiply by 10, we have a 90, and add the 9 in, get the 99. Now, after the dot, I mean, to do, rely on the fact that we always have one fractional. Let's just now not really bother with that and do the second loop. And here, this is the fractional part. We do the exact same thing, and the fractional length is now so if dot minus stir. Now the fractional length is, I think, fractional length is equal to stir length minus integer length and then minus 1. I think this is true. Let's see, fractional length I plus plus. We do the exact same thing. Fractional times equals 10. First U8 digit is equal to stir at it's dot at I plus 1 minus 0. We theoretically we should also validate this, like assert digit is greater than or equal to 0 and digit is less than or equal to 9. Like, we should do that. Let's just do that for now. I mean, we are guaranteed, theoretically we should be guaranteed that this should not happen, but let's just be safe for now. And we get fractional plus equals digit. And in the end, we aggregate this and we say result is equal to integer plus fractional times 0.1. All right. I have no idea if this works. Let's just see what happens. So let's say parse temperature. We start at semicolon plus 1 and temperature length, and we get F64 temperature is equal to this. And let's print the temperature as a floating point value. Temperature yeah, so this parses the correct temperature. Although it's probably not that fast, it works. Hopefully it works. Temperature, let's just do one fractional. Yep, let's turn this off for now. And now we don't want to break. We set the cursor to the new line plus 1 and see what happens. Yeah, now throughput is not used. Okay, so we got a problem. So after a couple of correct parsings, I think head-n10. So we fail after Saint-Pierre because we have a minus. Yeah, we haven't considered the case where there is a sign. So, okay, so U32 sign is equal to stir at 0 is equal to the minus sign. And here we do, so if result is equal to sign question mark, ternary operator. So if there is a sign, it's negative result, otherwise it's result. And we also stir. So stir is equal to sign question mark stir plus 1 stir. Still doesn't work. Okay, let's go into the debugger. Hopefully this works. Let's see. Let's stop and let's go into parse temperature. Let's launch this. Oh, we have to obviously build with debug symbols. Okay, let's do it again. Okay, now we are here. Let's remove this one. Okay, so sign is 0. So stir, let's look at stir, 0. Okay, let's continue. Let's continue. So now we have the negative 1.5. So sign is now true. Stir, you can see stir is a minus. Now stir is 1. Okay, stir length. This is also not true. Let's do an if here. So if sign stir plus plus stir length minus minus. Okay. Yeah, we had to subtract from the stir length. That was the problem. Okay, so next problem. Oklahoma City. So which line? Let's keep a line count. Uses for a line count 0. So let's say line number and line count plus plus. Okay, line number 16 head dash n 166 Oklahoma City. One zero dot plus 1. Where's, okay, which assertion is hit? It's 1, 2, 3, 1, 2, 3. This one in the fractional. What the fractional? So if our, so we have the dot and the end. Stir minus integer length minus 1. So if stir length is, for example, 4, 1, 0, dot 0, that's for characters. And we got dot minus stir, which should be which should be 2. So this should be 1. Dot plus 1. Dot. Hind character dot. Okay. I wonder why this happens. New line. Cursor is equal to new line plus 1. New line semicolon plus 1. Why does it fail? So what is, so if digit less than 0, or I mean that can't really happen, right? This is an I. Less than 0 or digit greater than 9. Let's see. Let's fire this up in the debugger. Oh yeah, we don't have false. Assert 0. Okay. Let's go here. Let's debug. Let's remove this. Assert 0. So let's look at, okay, fractional length is overflown. Stir length is this wild value. Why is stir length this value? So stir is 10.5 new line. Semicolon plus 1. Oh, this is not correct. Semicolon plus 1. What did I do? Semicolon minus cursor. This is not correct. This is end cursor minus this. Yeah. As you can see, this now parses the file. We have the length of the city. can parse the temperature. And as you can also see, it's, I mean, if we print every line, let's not print every line. Maybe, okay, line count is not used. And line count. Line count. Temperature is not used, whatever. If we run this, it probably will take a while. So let's put these asserts back in. Greater than equals 0 or and less than equal to 9. And let's also make this an I8. Okay, this will take a while. To do on a single thread. You know what? Let's put in the time command here. I will go to the toilet. Let's see. Let's see how long this will take. Like this. Let's see. Okay. Okay, so we were able to parse this in 1 minute and 2 seconds without doing any shenanigans. Now, the 1 billion row challenge requires us to store this information for each city. For each city, we have to store the temperature, the minimum temperature, the average temperature, and the maximum temperature. 1 B or C. Let's see. I think it's min. Where is it? Where is it? Calculate average. Running the challenge. Rules and limits now. Yeah, it's min, mean, max. Round to 1 fractional digit. All right. So, we need some way of storing for each city the appropriate min, mean, and max values. Now, how do we do this? Probably we should use a hash map. Now let's implement a very, very simple and stupid hash map. Let's have a record type, struct, and struct record. Now a record has a city name, and that has a length, and it has a min temp, a mean temp, and a max temp. Now we could calculate the mean incrementally. Let's see, incremental mean calculation. I think this is possible. Yeah, so this is how you can do it. But then we would require all these things. So what we could do is store a count and aggregate in the mean temperature and then divide by the count in the end. This is probably how we are going to do it. Yeah, maybe we don't. I don't know. We could compare these two. Maybe we should create a string type. Struct string u8 star pointer and u64 length, and then we can have a string city name. Nice. Let's put that up top, those two. So here we have our struct definitions. And let's also say find character. Find character maybe also takes a string, I don't know. parse temperature takes a string. Whatever. Let's just leave it like this for now. Let's say u8 star temperature start is equal to semicolon +1. Temperature start, or temp stir as temp stir and cursor minus temp stir. Then we can use just this temp stir and temp stir here as well. All right. Now, let's make a very easy and stupid implementation of storing records. Let's say before this we want to have some records. Now maybe we want an allocator for this. Okay, let's so we don't want all records to be on the stack probably, which is why we should probably allocate some memory. Let's use malloc for now. Should we use malloc? Okay, let's do something else. Let's implement an arena. So type def struct arena, struct arena, and an arena has a base pointer. An arena has a size, a position, and a size. You could also add a commit size, but reserving versus committing pages. Linux. I don't even know if there's a big difference. Let's just keep it like this for now. Let's say void arena push size. We have an arena star arena and u64 size. Let's say this returns a pointer. Now if so, u64 new position is equal arena position plus size. This is basically just a linear allocator. And new, so if new position is less than arena size, let's say void star result is equal to null, return result. Now new position, let's also do something like arena init u64 size, and we use mmap here. Okay, new position less than arena size, then we say result is equal to arena pointer plus arena position, and we say arena position is equal to new position. Yeah, that's already it. Then we can put some macros around it. Like for example, arena pound define arena push struct. It takes a T, a struct type, the arena, and it then does this T star, arena push size, arena size of T, arena push array, the arena push size, arena, and we also want n size of T times n. And maybe we also want to say push size 0. So this will then memset, I don't know, memset 0. We could also say, okay, for I0. If we don't want to use that, memset, let's just use memset. Memset result 0 and size. Now push size 0 is void star result is equal arena push size, arena size, and then we just append a mem set result 0 size, return result. Because we want to maybe 0 initialize all of our records. Now, arena init I don't know, maybe like this. mmap null length is size, and this is how do we round to the next power of 2? We add let's also pound define align pow2 a b, and then b is a power of 2. We do a plus b minus 1, and we want the top bits, which is AND together with not b minus 1, I guess. Is this correct? A plus b minus 1 and not b minus 1. So we could also use alignment here, align pow2 size and then page size, and let's say page size is kb4. Or aligned size. I think mmap does this automatically. But whatever. So align size and prod read map private map anonymous -1 0. This is arena pointer, arena size, arena position is equal to 0. Okay. And we can also use these push struct 0, push array 0, push size 0, push size 0. Okay. So with that out of the way, let's add an arena to the thread context. Thread context, arena star allocator, or arena alloc. Thread context. Okay. We could also do it like this, arena init, and return a pointer to the arena by saying, so this is the pointer, and the arena star arena is equal to the pointer. Now, arena pointer is equal to pointer, arena size is equal to size, and arena position is the size of an arena. Now the first thing of that is now an arena, which makes it pretty convenient for us to put it into the thread context. And context alloc is equal to arena init, and let's say it has like 64k. Does this build? No, it does not build. Arena init, because we still have this argument here, we can just remove that. While loop outside of a function. Oh yeah. Okay, so memset is not, we don't have memset. So let's quickly just hand roll memset, void memset, u8 void star pointer u8 value, and or maybe like this, u8 value u64 length for I0 I less than length I plus plus, pointer at I is equal to value. Memset, okay, let's say it's called memset. Line 90, return arena. Okay, record. Now we want our records, let's say this is arena push array record, and let's say we just push 32 times 32,000. Okay, let's say our lane count, where did we define that? Let's pound define map size as 32 times 1024, and 32 times 1024, 32 times map size arena push array 0. So these are our let's change the API to have arena as the first argument. push array 0 and its context arena. Yep. Okay, now no member named arena. Oh yeah. We named it alloc. Okay, now we only have warnings. Okay. So we are now doing a pretty simple thing. Where's our mem set? Let's say void now u32 string equal. So this takes star a u8 u64 len a u8 star b and u64 len b if len a is equal to len b, result is equal to 0. If len a is equal to len b, we go through I in u64 I is less than len a I plus plus. If a at I is not equal to b at I, we break. If we go through this and everything is the same, we say result is equal to 1. Okay. So let's go back to our record. Now record. So we have a city which starts at the cursor. What we are now wanting to do is just keep this array and iterate through the array, try to find something, and yeah. So what we do, so usually you would retrieve an index first based on the string. Records, insert record. Okay, let's say this is a void. We have our record star records. Then we have this, the u8 star city star and u64 city length, and we also have the x64 temperature. Now, what we do is typically first calculate a hash based on the city stir and the city length. Now, we make it pretty simple for now. And just return 0 all the time. Now this is our index. Map size. This is our index. Map mask. We can also define the mask. Because we have a power of 2, we can use a masking to get the right index into the array. So this is the digest, and let's say the index is equal to digest and together with the map mask. This will chop down the index into the range 0 to 32. Okay? this only works because we have a power of 2 of the map size. And then we do a linear probing. So we go for, we also probably need the length here. Record struct record. Let's say type def struct record map struct record map. We have our record star buckets. We have bucket count. Do we have something else? I don't know. Theoretically, we don't need this. Because we have to find it here, we could just do U64 record index 0, record index is less than map size. No, we start at the index. We start at the index. Index is less than map size, index plus plus. So the record is equal to records at index. Now, if there is no record in here, so if record pointer is not set, we can just insert into here. We can say record pointer is equal to city_stir record. How did we define the record again? Oh, as a string. Yeah, that's a problem. City name. So we could do city name pointer. String star city name. So if city name pointer is not set, yeah, I don't know. We can set it to a string where the pointer is equal to the city_stir and the length is equal to the city length. I don't know if we actually want to do it this way. And we can also set record min temp equal to temperature, record max temp temperature, record mean temp equal to temperature, and record, I think, what did we say? Count, record count equal to 1. So if there's already a record, we have to check whether the strings are equal. So city string. We could actually put this here. City string is equal to string dot pointer city_stir dot length city length. City string. Now maybe we don't want the pointers to the strings to point into maybe we don't want the strings to point into the original file. Maybe we don't want that. Maybe we want a string backing buffer. Here. Which we could easily implement. But let's for now keep it this way. So string equal. If string equal. Oh no. Okay, so this is city string dot pointer. City string dot length. We should do this. String city name, our city name, record city name, our city name dot length dot pointer, our city length dot city name dot length. So if they are equal, we want to do something. If they are not equal, we continue. So here we can say we want to break, and here we can say that we want to break as well, but otherwise we want to continue. So we're just iterating through the records until we find an empty one. And because we have the hash set to 0, it will always start at 0 and go through the entire array. Now, if the string is equal, we want to say let's make some macros. Define min AB. A is less than B, then A, else B. Max. Do it the other way around. Okay. Where's insert record? Here. So if now record min temp is equal to min of record min temp and temperature. Record max temp is equal to this. And record mean temp is equal to plus equals temperature and record count plus plus. And then we break from the loop and return. Now let's return a U32 from here. U32 result, which is 0, and result is equal to 1. Result is equal to 1. And return the result. We do this because if the map is full, we have a problem. Right? If it goes through all of this and the result is still 0, we have a problem because we ran out of space. Now, what we now do is insert the record. And assert that this is equal, that this is true. U32 not full. And assert not full. Now insert the record into our records. City stir, city length. So this is the cursor, city length, and the temperature. Is that it? Okay, mask size, map size, Okay, this already builds. Now in the end, when we pass through all of this, we have to go through all of the records again. Record index is less than map size. Record index plus plus. We have to go through all of them again and say, okay, record star record is equal to records add record index and record. A lot of records here, a lot of records. We say record mean temp is equal to record mean temp divided by F64 record count. Now, we can say, okay, if record count, we do this. I don't know if we want this branch here. Theoretically, we we cannot divide by 0. So we could divide by 1. Whatever. Okay. So let's see if this works. Segmentation fault. Okay, let's go into the debugger. I think we have a problem with our arena initialization. Where's our main function? Here. Let's just, okay, do we have a breakpoint here anywhere? Oh yeah, here. Let's turn it off. Let's go here. And let's make a breakpoint here. All right, I think we don't even need that. Let's step through the code. All right. Segmentation fault. So what is aligned size? Aligned size is correct. mmap null align side. Let's look at mmap man again. Prod read, oh my goodness, prod write was missing. Let's do it again. Of course, this time we write to the page. Oh, and we have to build. No. Prod. Yeah, now it's there. Build the stuff. It's still seg faults. That's bad. Let's make a breakpoint here. Where does it seg fault? Wait a second. Let's remove the breakpoint. Let's run. Ooh. What's length? Yeah, length is too large. Okay, 64K are not enough. 64 KB64. Let's make it 64 megabytes. Yeah, our arena was too small. Time 1 BRC. Now we want to time all of this in the end. But for now, let's just see how long this takes to do it in a very, very naive way. Just ignoring the bytes and returning a hash of 0 is obviously bad. But let's just see how long it takes. Let's just see how long it takes. I would say it takes about, I don't know. Hopefully we have lane count set to 1. I would say it takes about 4 minutes. Maybe, okay, maybe even more. I don't know. This is a very, very naive implementation. On one thread, without a good hashing function, just the linear probing. Yeah. This will take a while. This will probably take a while. And there the results are. All right, it takes 2 minutes and 6 seconds. This is not that bad actually. For a naive implementation. Now, how do we verify that our results are actually correct? Let's go here and let's just make a breakpoint. Before we return. Let's see. This will again take a while. Now we have the baseline. We have the baseline here. Oh. Baseline. For example, okay, this is even ordered. I don't know if that's a requirement, but okay. Let's see if we can get the same results. Maybe we're wrong. don't know how long it will take in the debugger. Maybe not that long, I don't know. Yeah, so maybe we can make a quick recap of what we did. Basically, we are parsing. So we have this entry point function, which is, oh no, okay. We can look at this in a second. We have the entry point function. The entry point function is basically the entry point for each of the threads. Right now we just have one thread. We get the lane index, and by the lane index we determine where our chunk starts and where the chunk ends. Now, then we create an array of records. A record is basically a city name, the min temperature, the mean temperature, and the max temperature with a count. And then we go through the entire file with our current cursor until we are at the end cursor. We are finding the next semicolon. Therefore, we know how long the city name is. Then we find the next new line. Therefore, we know how long the temperature is. We parse the temperature using the parse temperature function, which just goes through, finds the dot, it knows how large the integer part is, how large the fractional part is, and then it multiplies by 10 and adds a digit each time. And yeah, then we insert the record using the insert record function, which at the moment uses a hash function that just returns a 0. We mask the index into the allowed range of records, which is at the moment 32k. The challenge said we can have up to 10,000 of these, so 32,000 will probably not cause any problems. Right. So we go through, we start with the index, we look at the record. If the record is not set at the moment, we just insert our record with a count of 1. We set the result to 1, which means we successfully inserted. Then, if the city name was set, we compare the two city names. If they are equal, we min and max the temperatures, add to the mean, and add the count. Now, when we are done with all of this, we normalize, we divide by the count for each record if the count is greater than 0. Now, do we have the correct results? This is now the question. We go into our baseline. So these should be the values we should see in our records. Yeah, let's look at the first record. The first record has the city name Y. Now, so this is Yinshuan. Yinshuan is the first record. Shuan. And as we can see, Yinshuan is not correct. Now, this is obviously pretty curious because it's also pretty far apart. Now, obviously, something has to be wrong then. Count is also pretty high. I mean, can we watch records 10? Oh. Let's look at the second one. Second one has city name Skopje. Oh, shit. Skopje. Now Skopje, also not correct. Yeah. Now, this is the question. Is this the correct baseline? So I want to, how does ripgrab again work? Okay, ripgrab. We want to find Scopia in measurements of text. How do we get the count? Man RG count. Limit the number of max. Do we have to pipe this into? Okay, this is the count for Scopia. What count do we have? We have a different count. This is 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Now, why do we have such a large count? This could be push array. Push array. Push size. Now, is this completely 0? Push size 0. Push size 0. Memset. This seems incorrect. 1, 2, 3, 1, 2, 3. So 210 million. $2 million. I mean, 2 million cannot be true, right? I mean, if we have 10,000, then we have 20 billion. Yeah, it can be. 2 million is like more in the range, right? So clearly something is off here. Well, let's just step through code. Let's go here. Let's go here. Let's run. Continue. Okay. Right. Where's the cursor? Okay, temperature is 0.5. This is correct. Now insert record. Step into city string. City string. Yinchuan lang 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. This is correct. Now index is 0. Record. Now this is all zeros. Okay, this is good. we insert Yinchuan. So this is correct. What? Okay, something's off. Wait a second. Let's build. And let's launch again. Something's off. Temperature 0.5. Skopje. $27.3. Let's look at records. Records. No. Records at 1. City name Skopje. Okay. Now we have Moscow. Moscow with a 6.4. City string Moscow 123123. So that's 6 is correct. Index is 0. Record is Yinchuan. Pointer set. String equal is not correct. Skopje. Record. City name Skopje. String equal. Our city name Skopje. City name Skopje. What? City string. Our city name is Skopje and city string is Moscow. How does string equal return a 1? II not equal BI. Oh my goodness. This break. Go. Let's just return 0, whatever. Okay, that was stupid. All right. Let's do this again. Hopefully it now works. So let's run it again. Let's run it again and see whether we can actually get the correct result. This will again take some time. Let's look at btop. Yeah, it uses some CPU. What I find fascinating is that we only run at 20 watts. So this is, I don't know. Yeah, so where were we? Insert record. Now for this here, we want a nice hash function. So one to do is get a good hash function. Next to do is, do we want to store the records like this? I don't know, but maybe that's not even the first to do. The first to do would be to look at the individual timings of these functions. So how much time do we spend in insert record? How much time do we spend in parse temperature? Find character maybe. Yeah. And for this we have to implement, so let's see, records. This looks better. Baseline yin shuan. It doesn't look better. It does not look better. Did I build? Please tell me that I build. Still way too many. Let's check the logic again. Return 0. Oh my goodness. Okay, let's do it. Result 0. And let's go to return, go to star equal string equal return. It's still wrong. Oh my god. Okay, so let's do it one more time. Let's do it one more time. Oh, where's the breakpoint? Here. So we use this go to skip this. We could also just use a Boolean variable for this. It doesn't really matter. So first, to do. Let's collect some to-dos. To do. Collect metrics on the existing code. Okay, now we are. Where are we? Records 10. Okay, now it runs. Collect metrics on the existing code using RDTSC. Next thing, implement a hash function. Parse temperatures as integers. Collect metrics on the hash table. Average probing sequence length. What we probably also want to do is a back of the envelope calculation of how fast we could be. Now, does this still run? Let's see, hopefully it works. So, how fast can we deliver the data from the file cache disk We saw that we can parse it at 5.8 gigabytes a second if we just touch every byte and count. So this may not be the limit. Did it do anything? Let's see. So, it still runs. What is it doing? Mr. VS Code. Let's see. I will make myself another cup of tea and then we're gonna continue. It's still running, right? Come on. It seems to be a lot slower now. And this is probably because we fixed the string equal function. Okay, maybe okay. So we can work while VS Code is still doing some stuff here on the side. We can work on profiling this code. Okay, how do we want to profile this code? I probably want to tag this like this. This is why yeah, every time I save, VS Code is also updating. I want to say something like profile function. And end. Something like this, profile end. Now, how do we do this? We know that we want to collect an RDTSC at the beginning and at the end. So let's make something like, how do we do this? How do we do this? So what we certainly want to have is something like a type def struct profile zone. And the profile zone probably has something like a hit count and a inclusive time. And maybe also something like a child time. Maybe this thing also has a name. A const char star name. Then we have a static array of these, profile zone. And we should probably have this for each thread. Profile zone, profile zones, zone count. Let's say we can have 16. Let's also say that each thread has profile zone star a profile zone stack to keep track of the individual calls inside these zones. And also pound define zone stack count as 512. I don't know. Zone stack count. Now, our begin do we refer to the zones as names? Probably yes. So void begin, we probably also need a zone stack index, which is initially 0. Begin profile or enter zone. Now what enter zone does is it takes a what does it do? It probably takes a name and wants to compare the two. Then it wants to go through all of the profile zones, maybe also have a profile zone count, which is initially 0, for zone index this can be your 32, zone index 0, zone index less than profile zone count, zone index plus plus. This shouldn't be, it shouldn't be that much. This of course will introduce some overhead, but let's also implement U64 stir length, which takes a car star stir and it goes through the stir while stir plus plus is not equal to 0, using for result plus plus return result. I mean, we could also say that a profile zone has a string. And let's also pound define stir and then we do string dot pointer is equal to stir dot length is equal to size size of stir. I think that works. Or just maybe don't. Maybe just keep it const car star. Okay, string equal name strlen name. Okay, profile zone star zone is equal to profile zones at zone index. So if zone name strlen zone name, it's pretty sloppy. So if they are equal, if the two are equal, say if zone name, if this is even set, can be null. If it's not set, we just say zone name equal to name. Zone, all the other stuff is, okay, zone hit count, maybe start time. It's still running. How can this still run? What the heck? Zone name, zone start time, RDTSC. Zone yeah, that's enter zone. Also, if they are equal, we set the start time. We could, okay, profile zone, get zone. We go through all these zones. We don't do this. Profile zone star result. If the strings are equal, zone is equal to zone. Result is equal to zone. Break. Result is equal to zone. And break. So we find the zone. Return result. So if we have to make a new zone, we say profile zone count plus plus. And enter zone gets the profile zone. Get zone by the name. Zone name name, and then it sets zone start TSC start time to RETSC and void exit zone. No, this will then zone stack. How do we call it? Zone profile zone stack. Now profile zone stack add zone stack index. Maybe we first increment this. We first increment the zone stack index, then we store it at the zone stack, store the zone, so that here we can just retrieve the zone. like this. And then we can say, okay, the parent zone is equal to profile zone stack at zone stack index. So and then we say, okay, U64 end time is equal to RETSC, and U64 elapsed is equal to end time minus zone start time. Now we want to increment the zone hit count. We want to say zone exclusive time plus equals elapsed. We want to say zone and then parent zone child time plus equals elapsed. Okay. I don't know if this works. Okay, and then we can say something like, let's say pound define profile function. Now, how do we get function name clang function name macro func? Is this true? Function. Func is a macro, but it's not. Func clang. I don't know if it's func or function. We can just use the function name. And how do we stringify macro C? I think it's like this. Does this build? I bet you it doesn't. Zone IDX. Let's extract all of these macros to the top. Okay, profile function. Profile function should just call begin enter zone with this. No member named exclusive time. Profile zone. Inclusive time. Exclusive. It's inclusive. Zone index plus plus. Zone IDX. Zone IDX. Okay. Zone name. Profile. So profile zone doesn't have a name. Profile zone should have a name. Stir length. Stir length. Name. I don't know if you can actually do this better. I probably you can. Profile zone stack. We don't need this here. String equal. Call to undefined function. These should probably be at the very beginning. Okay, profile function. Profile end. Exit zone. Exit zone. Exit zone. These should also be at the very top. It's a little bit unfortunate that C requires you to have the functions in order. Now, incompatible integer to pointer conversion. Get zone. What? Is it because no. Profile zone. What did I do? Implicit declaration is here. Get zone. Get zone. Get zone has to be here. Oh my goodness. Okay. This is so shitty. Now these have to then. No, what? This is a curse. Okay, this is a curse. Because we put profile function in here. It creates a circular dependency. So we would need a header file here. We would desperately need a header file. Oh man. Okay, so we are almost there. String equal. Why is it still not working? Passing car star to parameter of type u8 star. Okay. Oh man, this is cursed. This is cursed. We're not very consistent. Okay. So let's go into parse temperature. And let's say profile function. Profile end. Okay. Can't you do this? You can't stringify this? That's unfortunate. This is a predefined string. Okay, so maybe func works. Ooh. Okay. We also want zone, enter zone. We also want to report, like profiler report, which prints out all the stuff. So it goes through all of the zones. For u32i0, I is less than program profile zone count I++. Then we get the zone profile zone star zone is equal to a profile zone. What was it? Profile zones. Profile zone. Profiler report. Okay, profile zones at I. And then we want to print f how do we format this? Let's just say, okay, %s zone name, then a tab, then we also need the CPU frequency, and then time inclusive seconds or seconds is equal to zone inclusive time over CPU frequency. Then we just put the seconds here, or maybe milliseconds. I don't know. Let's just do it like this for now. So zone name and let's report also the exclusive time. So inked seconds, exclusive seconds is the inclusive time minus zone child time. And then we do inc seconds, x seconds, and go into our main. Now go here and profiler report. CPU frequency. Okay, that's okay. So let's build it with O3. Let's see. 1BRC, whether this, okay. It's segmentation faults. Why does it profile function? So if I see, so this doesn't segfault. Let's see. Enter zone. Sixteen zone counts. Where does it segfault? This is the question. Okay, let's put it back in. Let's go into build. Let's pass in a G. And let's run it in the debugger, which should give us, which should put us in the right place. Okay. So zone is a null pointer. We should go into get zone. Let's see. So get zone is called with parse temperature. That's okay. Now, zone. What? Profile zone. Okay, I know why. Get zone. So profile zone count should be initially profile zone count should be initially 1. So if we do this now again, we go into enter zone. The zone is 0, zone count plus plus, zone name is equal to name, result zone, result is this. Now enter zone has the zone, which, yeah, this is correct. Zone stack index okay. So parse temperature is going through this. Okay, parent zone child time. Okay, we should initialize the zone stack So global zone. Global zone. Profile zone. Dot name. Global. Dot start time. 0 dot inclusive time. 0 dot child time. We may need an init function. Dot hit count. Probably also need one here. Profile zones is equal to global zone you know what? We just go through zone count. So this has global zone and then all zeros. Global zone. Incompatible pointer types. That's unfortunate. So do we need an initialization function here? Where's profiler report? Let's say void profiler init. Let's say profile zones at 0 is equal to global zone. Global zone. Oh no, profile zone stack. Profile zone stack. Oh. Global zone. That should work. Let's see. Yeah, so we have on the zone stack we have, or let's say root zone, root, and let's call it root zone. Now let's see. Profile zone. We put a new zone. We enter the zone. Profile end, and there we go. Say in the while loop, line count. Let's say if line count is equal to 100, we just break. Okay. So that's way too little. We should okay. Let's make 10,000. As you can see, we're spending some time in parse temperature. I don't know why this thing profile zone. Oh yeah, it should be 0. Yeah. Now we see parse temperature 0.0029 seconds. We could also report the cycles itself. And also this is not the average. This is just the accumulated time. So in theory, we should also have to divide this by the hit count. But okay. We could also global root zone. We could also report the percentage. I don't know. But this is nice. I mean, effectively what you can now do is put these things here like insert record and say profile function, profile and then we will see another one of these in here. Yeah. We may also want to report the global time. So profiler void profiler init, and we say root zone dot start tsc is equal to rdtsc, and then total time is equal to root rdtsc minus root zone dot start tsc. And then we can also report a percentage, like f64 percentage is equal to f64 zone inclusive time over f64 total time. And then we can also report a percentage. So do you do this like this? I don't know. Parse percent dot to f percent, that's 100.0 times this, and percentage. Start tsc root zone dot start time. It's also not a function. Root zone dot start time. Total time is that okay, it doesn't work because we don't call profiler init. Entry point, let's say profiler init, and there we go. We spent 79.08% in insert record. So that is the worst. That is probably where we spend all of our time. Now, if we were to run this on all, now do we want to report this as milliseconds is the question. Profiler report. I don't know. like 1000. Oh no, this is not correct. Like milliseconds. 1000 times. Oh no. Where's the line count? Line count. And line count is less than 10,000. And we probably also want to report the average profiler report. The average, which zone hit count, F64. Let's say denom is equal zone hit count times CPU frequency, and then cast this to an F64, and then we don't have to do this. Denom. Okay, so we spent almost no time here, and 0.015 milliseconds on average in insert record. Now let's only report the inclusive time for now, and microseconds. Let's get that symbol. All right. And so let's 1000 times. Oh, we can also do macros 1. We had this macro. It has to be good for something. Hey, 1.4 microseconds in insert record, 0.0286 microseconds in parse temperature. Maybe we don't want this here. So let's say if def report prof report average, else and if. And then we report in milliseconds. Yeah, I don't know. Micros we can put it in there over F64 millis 1. Yeah, whatever. Okay, so let's run this entire thing, and see what we get. How long will it take? We probably spent, yeah, I don't know. We probably spent way too much time in the insert record function. So this will be the final run. Do we want to profile something else as well? Maybe. I can also show you something I have borrowed from the raddebugger, which is we have this profile function here, and we can also make a macro profile scope. Now profile scope gets a name, and profile scope has a very nice trick because it uses a for loop. We can use I0 is equal to enter zone with the name comma 0. This comma operator evaluates all expressions and then assigns to the last one. And therefore we can do this. And I not equal to 0, I plus plus, and then we can finally use profile scope as well. So if we say this is a profile scope, and this has the name normalize get mean. Okay, it takes too long. It just takes too long. Can we? Oh, yeah, sure. I plus plus. It should be underscore I. This is completely borrowed from the raddebugger source code. You should check it out if you want some cool C macro tricks you can borrow from them. Let's see how long this will take. We also have to check our results again. We should do something like, okay, record 0. It's the name. The min mean and average, and then record city name dot pointer, record city name dot length, record min temp, record mean temp, record max temp. It's running. Field position should have type int. Okay, let's see. We probably also have some profile overhead here. Which is fine. But this is the basic setup. We can profile functions, we can profile scopes, and from there on we can improve our very, very bad implementation. Maybe we should check whether it's even working on a smaller line count. And line count is less than 10,000. Okay. So get mean is basically free, but you can see it shows up here. And we can also see this. 100 so this is very weird. 185.6 as the mean. Insert record. We should also print the count and times percent LU record count. $28 times. I don't know. Yeah, so let's execute it a final time on all lines. This will probably take a while because our insert record function is very bad. So the first thing that we can see before we even remotely think of changing parse temperature is to really look at insert record. Let's see how long this takes. Profile report. Let's also just put a nice profiler report. Let's put a tab here. All right, this will now take a while. And we compiled it with 03. Let's see if we can at least get the correct answer for Yinshuan. Come on. is really struggling. It's really struggling. It feels like an eternity. It's so slow. Oh my god. We haven't even, I mean, okay, we combine the thing automatically in the end, but yeah, we've done quite some work here. We have now a working, hopefully working, we haven't really validated it, profiler. There's also a new line missing here. 10 gigabytes. Yeah. We can also turn off the profiler if that does anything. I mean, the problem we have is that also for the profiling we do these Sterling stuff. We probably have to measure the difference in execution time with and without profiling, because it probably will make a difference, especially because we hit this 1 billion times, 2 billion times, because we have 2 times these zones. So what we could do, for example, is so if def profile prof enable, these all turn to this, and else they're just empty macros. So they don't do anything. And there it is. Yeah, see the mean temperature. Okay, so this now is correct. This makes me, I think this was correct. Baseline.text. So yin xuan. See, we correctly get the min and the max, but we don't get the right mean. Now, why is that? Why is that? Mean temp. This is really interesting. We increment the count and set count to 1. Now, is this because it overflows? It may overflow. When we increment the count plus equals temperature equals the temperature. How do others do this? Do they update it incrementally? So we had 2 million times, let's say, 2 million times. So this should be, I mean, why is it such a large number? Why is it such a large number? Mean temp. Oh my goodness. No. 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 It should have been divided by this. Map size. So what if we divide this here? 21773.685.3 over 24204. No, that doesn't work. Oh, it is 9. So it didn't divide it correctly. Didn't do this. This might be because of our profile scope. So this is exit zone, and we can look it up how they did it in the raddebugger. Raddebugger. They had it in source, base, threads, base, core, profile. Oh, here. Profile. Where was this defer loop? Base core. Defer. Yeah, here. Defer loop. Ah, this is how they did it. This is pretty clever, but okay, let's see. So they did like we did. Not oh my goodness, yeah, of course. This was stupid. I plus equals 1, comma, exit zone. Now build. Let's do a timed run. Let's do a timed run. Prof enable. Prof enable is not set. So it shouldn't put the profiling in there. Profile report. Where's profile report? Profiler report. So this should also not work. Yeah, this will crash. Okay, whatever. Okay, last run. Last run. And then we are done for today. What do you think? How long does it take? Who knows? So one thing we should obviously do is test the overhead that we introduced by using the profiler. Also, we should probably use a hash table for the profiling as well, because we're iterating through the zones all the time to find the right one in enter zone. We could also store last. Nah, that won't work. That won't work. Let's see. How long does it take? The CPU is working. Now 1 billion rows is a bunch of rows. Who would have thought that? Oh. Oh man. Now some solutions I have seen parse this even in Java in like under a second. Which is pretty wild. I mean, it was a better machine, but honestly, we're executing on a single thread, and yeah, this will take almost as long as it does take right now on a beefier machine. So I think by looking at the memory footprint here, we can see how far we got. See how slow we are? Like we're parsing like 100 megabytes a second. Like now we're at 10. 3 more gigabytes to go, or so. $11 gigabytes. See how the kernel swaps us? Now we're on this core again. We should be almost there. Oh, we're done. It took us just 6 minutes. And our mean is 0. Our mean is 0 because we divided again. How can one be? How can this happen? Like, oh my goodness. And as you can see, we spent 48.14% in insert record. So the next time we're gonna go and look into insert record and why insert record is so slow. Now, I will eat something and then we will see us again. Sometime, somewhere else. I wish you a nice day.